Hello everyone. In this video, we are going to understand a very important concept in SAR data processing, the difference between averaging in decibel scale and averaging in linear scale using Sentinel-1 data in Google Earth Engine. This is a very common mistake where users directly calculate the mean of SAR images in decibel scale. However, this approach is scientifically incorrect. So first, let's understand the concept. Sentinel-1 SAR data is provided in decibel scale, which is a logarithmic representation of backscatter intensity. But averaging should always be performed in linear space, not in logarithmic space. So, if we directly average in decibel scale, it distorts the physical meaning of the signal. The correct workflow is: first, convert decibel to linear, then compute the mean, and finally convert it back to decibel. This ensures that the result represents the true physical backscatter. Now let's move to the outputs and understand everything step by step. Output 1. Wrong VV decibel average. This output shows the VV polarization, where averaging is done directly in decibel scale. Here the image appears noticeably brighter in many regions. The bright white tones indicate higher backscatter values, especially over urban and rough surfaces, but these are actually exaggerated. The river is visible as very dark black, which correctly represents low backscatter, but the surrounding areas look overly enhanced. This tells us that the wrong method is artificially increasing the intensity values, making the image less reliable. Output 2. Wrong VH decibel average. This is the VH polarization using the same incorrect averaging. Here, the image appears overall darker compared to VV, but you can clearly see a grainy and noisy texture. The dark grey to black regions represents low backscatter, while lighter grey areas represent vegetation, but the pattern is irregular and inconsistent. This indicates that the wrong averaging method is introducing noise and distorting the natural structure of vegetation signals. Output 3. Correct. VV. Linear average. Now this is the correct VV composite, where averaging is done in linear space. Here, the brightness is more balanced. The white areas still represent high backscatter, but they are no longer exaggerated. The grey tones transition smoothly, and different land features are more clearly defined. The river remains dark, but the surrounding regions now look more realistic and physically meaningful. This shows that linear averaging preserves the true backscatter characteristics. Output 4. Correct. VH. Linear average. This is the correct VH composite. Compared to the earlier VH image, this one is much smoother. The grey tones representing vegetation are more uniform, and the noisy appearance is reduced. Dark areas still represent low backscatter, but now the transitions are gradual and consistent. This confirms that linear averaging significantly improves data quality, especially for VH polarization. Output 5. VV error map. Wrong minus correct. This output shows the difference between the wrong and correct VV results. Here, the colors indicate the magnitude and direction of error. Blue regions represent areas where the wrong method produces lower values than the correct method, while red would indicate higher values. White areas represent minimal difference. In this image, most of the visible areas are blue, which means the wrong method is generally underestimating the VV backscatter compared to the correct method. These blue patches are scattered across mixed land and river adjacent regions. This highlights that even if the image looks brighter earlier, mathematically it can still produce underestimation in many locations. Output 6. VH error map. Wrong minus correct. This is the VH error map. Here again, blue dominates the image, but it is more intense and widespread compared to VV. This means the wrong method is causing stronger underestimation in VH polarization. The blue clusters are more concentrated in vegetation and complex surface areas, indicating higher sensitivity of VH to incorrect averaging. Very little red is visible, which means overestimation is minimal in this case. Finally, the statistical results show that the error typically ranges between about 0.5 to 3 decibels, which is significant enough to affect real-world applications. So, to conclude, Averaging directly in decibel scale is incorrect because it operates in logarithmic space. The correct approach is to convert to linear scale, compute the mean, and convert back to decibel. This ensures accurate and physically meaningful results, especially for applications like flood mapping, vegetation analysis, and change detection. Thank you for watching.